this is organization, a global company today with around 2,400 plus engineers. And this company was started in 1987 in Peoria, Illinois, but since then it has expanded a lot. And as you can see in the bottom right, you will see the where all we are present. In North America, we are present in a couple of locations in addition to Europe, UK, and Asia Pacific as well. Our majorly our business is divided into three major sectors: aerospace and defense, heavy engineering, and automotive, energy, and medical devices. So basically, as you can see, we have our major clients are Caterpillar, Siemens, Airbus, Daimler, Bombardier. So we have some presence in Canada as well, in Montreal, where we serve one of our premium customer, Bombardier, there. So what we basically do today is providing product engineering solutions for in the sector of mechanical engineering, or whether it is digitization, which we will speak more about the manufacturing engineering today. So in this slide, you can see we are serving in the areas of aerospace, defense, heavy engineering, automotive, energy, and medical devices. So we have the right product knowledge. We provide the engineering solutions in the whether it is in the at whether it can be at on-site or it can be offshore, depending on various business models. But the whole idea is providing any kind of engineering in the entire product life cycle. Anything related to engineering world, we provide the solutions. So maybe I can provide more details if anyone wants to know more about our organization. I will leave a contact details after the end of the presentation. I will be very open to introduce or provide more details about our organization. I will allow Murari to take over and focus on the actual subject today, and looking forward to it. Murari, if you want to take it up.
Thank you, Sanjay. Thank you very much.
Thank you.
Good morning. Good morning, everyone. Nice to have you this morning in this webinar. I am Murari. I am currently an advisor for Access Cadets, helping develop business strategies for them. I have been in this role for the last few years, but prior to that, I was heading the global manufacturing solutions organization for Caterpillar. So we used to support more than 55 factories and product groups of Caterpillar worldwide, helping improve their time to market. So today, I'll be taking you through how virtual product and process development can help not only mass manufacturing companies, but also companies that produce custom-built machines. VPPD, or Virtual Product and Process Development, is also called as digital manufacturing in today's world. So all of us know that CAD has evolved, computer design has evolved over a time period, and today almost every design that we do exists in a 3D environment. So that is with that advantage, the VPPD has also evolved because of the excellent visualization capabilities that these tools provide to us as developers. So to define what VPPD is, it is an integrated computer-based system which has got inherent simulation capabilities, excellent visualization, and analytics capabilities. On top of that, it also helps us to collaborate. So there are several examples where in my past career, I have seen teams sitting 10,000 miles away work together in a collaborative manner to evaluate a concept or a design from a different standpoint, say manufacturing, assembly, cost, and all those. and help develop better designs, and also help companies to launch those products on time at a lower total cost. That's the greatest advantage that we can uh, get from this VPPD initiative. So there are some of the benefits that have been listed on the screen. There are certain benefits that are very tangible, and there are certain benefits that are intangible. Whether it's tangible or intangible, but when we work on this VPPD environment, our virtual product and process development environment, we'll be able to realize one or more of these benefits. That is something that is the best thing that can happen through these VPPD initiatives. There are several examples in my life itself. Actually, when I was heading the Global Manufacturing Solutions division, I have seen factories enhancing their efficiency, whether even if it's a custom-built factory, where actually they will build machines specific for a particular customer requirement. So it will have a lot of variants. There will be a basic machine. On top of that, we'll be building many attachments on top of that. So even for those kind of environment, we have seen efficiencies improving dramatically through these VPPD initiatives. There are situations where I have seen that all the validations happen on the computer itself, and the machine directly goes for a pilot production rather than, so there are situations where we have done away with physical prototyping and went directly into pilot production. I also seen situations where both pilot missions and the production missions can be manufactured in the same factory environment without making any additional investment. So all these can be made happen through these virtual tools that we have today. So way back in 2003 itself, SimData actually did a survey and identified that there's a company that is investing on digital tools from a manufacturing standpoint can realize almost 5 times the benefits of the ROI. So when way back in 2003, this has been communicated, but now in this last 17 years, the technology has improved significantly, and with better connectivity and collaboration tools in place, we can see much more benefits when we deploy these VPPD concepts and tools in our new product development as well as the continuous product improvement programs. So all of us are familiar with the new product development cycle. So it all starts with a strategy or a concept, and it goes on until production. So in between, we have different stages through which the new product development program progresses through. We have different gates in which the designs, the concepts, the detailed designs, and the manufacturing drawings will be evaluated. So all these happens, then we get into prototyping, physical prototyping. Once the physical prototyping is done and we are convinced, then we get into the pilot manufacturing to ensure that the actual manufacturing situation is conducive for us to produce machines on expected lines. So all these happens, and then we come to the launch date. Okay. So in a typical new product development cycle, we go through all these phases, and the machine goes to production. It also happens on a continuous product improvement program, CPA programs. On the right, you can see the Deming cycle, the PDCA, where actually when we come across any issue or when we think of actually improving a product, we do certain things in a systematic manner and again relaunch the machine or the product into the market. So whether it's a new product development program or whether it's a continuous improvement program, you can still use these VPPD methodologies and tools for your benefit. The greatest advantage that we can see by using this VPPD tool is actually, it's well represented on on the graph below. So you can see the cost versus timeline chart, where in a traditional product and process development program, most of the activities start happening after the uh, drawings are released to production. So once the drawings are released, the manufacturing engineering or the process engineering team receives the drawings. Then they work along with the other stakeholders within the company to understand the design intent, and then start reviewing the drawings, decide on make versus buy decisions, and then put together process plans in place, get the material, and do the physical prototyping, pilot production, and then get into full scale production. But when they do the physical prototyping, they realize, actually, in the traditional methodology, companies realize that there will be a lot of issues coming up once the iron is received. So this necessitates the design teams to go back to the drawing board, make necessary changes, and actually it comes back to, again, a new set of parts will be manufactured and the physical prototype happens. It goes through these, it's an iterative process. So what happens in this traditional environment is the cost increases, because all the digital information is getting converted into physical information. So it can be iron, it can be plastics, whatever you have, in any commodities you have. So the companies invest a lot, and because of that, once we get the prototypes and we realize that there are issues related to the prototypes, related to those parts, then we have to go back and fix. So all these requires a lot of money to be invested, and it also results in time overruns. So the company might have decided to launch a particular product on a particular date, but because of these unforeseen issues coming up, the dates gets pushed, the cost increase, and that's what you see in a traditional product and process development. So the curve shaded with in yellow color represents that. You can see an escalation in the cost after the proto stage, and even the launch dates getting pushed. Okay, so this is a big worry for the stakeholders in any corporation. So how to address that? VPPD, or virtual product and process development, helps us to accomplish that in a much better manner. So what happens here is the product design teams and the process designers or the manufacturing engineers work together in a collaborative manner in the early phases of the new product development program. So it's also called concurrent product and process engineering, so which all of you are familiar with. So, but the advantage that we have is with CPPD and with the ability to have the visualization and the ability to see everything, see and use the 3D geometry and visualize everything upfront, the teams can make informed decisions. So any issues that are coming up from a manufacturing standpoint can be identified upfront in the early phases of the new product development program, and can be fixed there on the drawing board itself before it gets converted into a physical material. So there will be iterations, no doubt about that. So there will be a product interactions happening between the product and process teams. It will go back and forth, but all those happen in a virtual environment. So teams work together. There will be a greater level of collaboration. Issues will be identified upfront and fixed then and there before the manufacturing drawings are released for production. So because of that, the cost that we incur during the physical prototyping or during the pilot production gets diminishes, and companies have seen are able to experience product launches in a timely manner. So the VPPD really helps companies to bring products to the market at a much faster pace, and that is why we are seeing there's a lot of excitement to embrace these technologies in the automotive sector. But this is not necessarily meant for automotive, where mass production is involved, but also for companies which manufactures custom built machines. So with every mission that we have a custom requirement. So developing a physical prototype and validating that in a physical environment consumes a lot of time and money. But all those can be done at a much faster pace in the virtual environment. So this VPPD methodology not only helps mass producers, but also helps companies that produces niche products for a specific purpose. It not only helps new product development, it not only helps product and process designers, but it also helps those who are on the aftermarket segment. So for example, the product information that we get from the 3D models can be used effectively even for performing serviceability studies, help perform assemblies and disassemblies at a dealer site or a mine site or wherever it is. So all these can be validated upfront. That's the greatest advantage that VPPD brings to the table. So if you see here, the VPPD is well ingrained into into the NPI program, new product development program, particularly on product design and development, process design and development, product and process validation, and to certain extent, even on the production phases. So all of this in large corporations, this is effectively managed through a backbone, which we call as product lifecycle management, PLM. There are a lot of PLM tools which all of us are aware of, like Team Center Engineering or Team Center Manufacturing, 3D PLM, Windchill, and all those. So these PLM tools have got inside them embedded software applications which help you to perform necessary validation and visualization using a suite of applications. But the good part is these applications or software applications are available separately. It need not be embedded into PLM. If it is done inside the PLM environment, that would be the best thing to happen. But companies are not limited to have a PLM. They can have these applications, standalone applications, and still get the maximum benefit out of them. So these are some of the software applications and tools that are very prevalent today in the market. Siemens and Dassault Systems lead that effort. So they are considered to be the pioneers. They bring the best of the technologies for the use of companies to bring their products on time, every time at a lower total cost. But there are also other corporations like Autodesk, which offers a complete suite of products called Product Design and Manufacturing Collection, which helps any corporation to evaluate their designs from both design and manufacturing standpoint upfront. So there are tools like RAMSYS, which helps us to do ergonomic analysis. Tools like FlexSim, which helps us to perform distributed simulation and identify issues upfront, even before the physical build happens. Tools like a priori, MTI systems, and all those helps develop cost models to understand what would be the target cost of a new product, or it also helps us to prepare should cost modeling, where buyers or purchasing team can effectively negotiate with the suppliers and realize a better cost advantage on the parts that they produce with their supplier ecosystem. Tools like VSA, Valuation System Analysis, which is showing up on the bottom left of the screen, helps us to perform tolerance stack up. So in a design we have, based on the tolerancing, a lot of issues during the manufacturing stage. So if it is linear, we use 1D tolerance stack up. But in a complicated integration, where, for example, when we have an exhaust system integrated on one side with the engine and on the other end with the chassis of the product, so it will be in a 3D plane. Everything will be in a 3D, different 3D planes, and performing tolerance stack up for that would be difficult. And in those situations, this VSA, the Variation Systems and Analysis tool from Siemens, can really help us to accomplish that much better. ICIDO is a platform. It's an immersive visualization platform which can be deployed within a corporation. And if the same company has got multiple sites, manufacturing sites, it can be deployed across different sites. And teams, product teams across different sites can collaborate, and actually because of the excellent visualization capability and collaboration capability that ICIDO provides. See, so there are a lot of tools and applications available which really helps to embed VPPD, the virtual product and process development, into the new product and continuous product improvement cycle. When it comes to product development validation, it really helps us to transform ideas and raw materials that we can use into real products accurately and at a faster pace. So these visual tools that we have, which are part of the Siemens or Dassault or Autodesk suite of tools, can be used like a markup application. So we call them as digital markup applications. So like what we do on the by creating markups, physical markups to understand the concept design, we can really do that in a similar fashion using digital markup tools. So by doing that, whatever the designer conceives in his or her mind can be brought to life in a virtual environment, and everyone can see, appreciate, and add their viewpoints into that. So VPPD tools and applications helps us to develop concepts faster, visualize it in a much better manner, and helps to communicate ideas with different stakeholders. So once the concept is frozen, then it moves to the detailed product design stage. In this stage, the VPPD tools helps both product and process engineering teams to validate the design from an assembly manufacturability standpoint, DFMA. So it also helps to validate the designs from a costing standpoint. So this is here we can really understand whether a particular feature in the design is really going to add value to the customer or not. So a virtual tear down can be performed, and stakeholders from different teams can sit together and understand whether a particular design feature is going to add value to the customer, whether the customer is going to pay for that. If not, is there an opportunity for us to change or remove that feature, which can help improve the bottom line of the company. So all these analysis can be performed here. So it also helps the service teams to work very closely with the product designers to perform serviceability and safety studies. So once the mission is launched into the market, and during periodic intervals, the mission will be taken up for servicing. It can be defined service, or it can be something unforced, yeah, a breakdown where something has to be fixed. So all these kind of situations can be simulated or created upfront and visualized along by sitting along with the service engineers. So any issues that the design teams will come up during the servicing phase can be identified upfront and eliminated during the detailed product design stage itself. The other advantage that we have is performing ergonomic analysis. There are tools like Classic Jack, which is part of the Siemens tool, or something like Ramsys, which I mentioned a while ago. These tools can be used to perform ergonomic analysis. So it also helps us to predict on the operator if he or she is going to perform a particular task uh, so there are, it all complies with standards like NIOSH, RULA, OACO, OSHA, and all those. So we can get all these information, and if a need arise, if we see any ergonomic issue, for example, when we perform this ergonomic analysis, if we identify there's a stronger possibility of an injury on the spine, and so that information can be fed upfront to the both product design and manufacturing engineering teams, and these teams can go back to their drawing boards and make necessary changes, product or process, so that a potential injury can be avoided. So these VPPD tools helps you to perform all of these analysis well in advance, so that there won't be any issue when the product is manufactured in a factory shop floor. Okay, so now with the after these validations, the design becomes perfect. Okay, and it goes to the next stage where the drawings will be released for manufacturing. So necessary tolerance analysis can be done. It can be 1D TSU tolerance stacker, or it can be a complicated 3D tolerance analysis using tools like VSA, which I mentioned, or CE tool. So these tools really helps us to perform detailed tolerance stack-up analysis. So make necessary adjustments on the drawing so that there won't be any issues when we manufacture those parts to the drawing specifications. So at the time of integration, the issues that the operators face in a traditional environment, we minimized dramatically by using these tolerance analysis tools. The drawings are released and it goes for production. But along with that, the companies have to create the technical content for the aftermarket. So the advantage here is with every information available in a 3D environment, 3D parts manual, service manual, assembly, disassembly procedures becomes much easier. The good part is even this can be published in a 3D PDF format, which can be enabled using Adobe PDF readers. So the files will be very lightweight and it can be circulated. It can be even seen on our mobile devices. So this is how actually VPPD helps on the product development and validation phase. When it comes to process design, development and validation, the benefits that we get out of this are immense. So as the models mature, as the 3D models mature in the product design phase, since all these are happening concurrently, the manufacturing engineering and the product engineering teams work together in a concurrent manner, the process designers can start creating their process plans even before the drawings are released for production. So which means All the process definitions can be made upfront. The teams can be ready for production at any point of time. So using the 3D information that we get, so it can be the engineering bill of material. The process designers can generate manufacturing bill of material and create a high-level process flow, and using that information can also perform time studies. So whether they will, we can use predetermined motion and time standards, PMTS tools like MOST, Maynard Operations Sequence Technique, or PCDMS, or anything of that sort, uh, and actually create what would be the cycle time for each and every process step and for the whole product line. So all these can be done upfront, and once those information are ready, then VPPD tools helps the process engineers or manufacturing engineers to perform detailed process design. The advantage here is because of the excellent visualization capability that these tools possess. For a given demand, the process designers can design a factory in a 3D environment and make necessary changes on that so that the material flow, the number of resources that it would require to perform the task, the way the material has to be presented at the point of use, how the process, the activities are to be performed, everything can be simulated and validated. Tools like FlexSim and PlantSim, or those discrete event simulation tools, helps process designers to simulate a future state in a mathematical, using a mathematical modeling, and predict what would be the throughput of a particular facility for a given demand, size, and investment. The advantage because of this is decision makers at the highest level in the company can make informed decisions. They can get to know what would be the capital investment that they have to make in order to produce a certain machinery or an equipment for a particular demand. So there won't be any additional investment. Everything can be simulated upfront using these discrete event simulation tools. And the best part is all these can be visualized in a 3D environment. So all stakeholders, irrespective of their level in the organization, can see, understand, and make decisions according to their roles and responsibilities in this corporation. So people in finance or leadership teams, before investing, they can use these tools and understand what would be the investment that they have to make. Investment can be equipment, investment can be on operators, resources who are going to perform those tasks. Investment can be on the facility space that they would require. Every piece of information can be validated for future, even for a future state. It can be, for example, if a company is planning to establish a manufacturing setup and start production in 2023, year 2023, and we are now in 2020. So 3 years from now, the company should be up and running and should be producing a certain number of equipments every day. So with these discrete event simulation tools, we should be able to design, simulate, and analyze for a particular date in the future and see how all these systems are going to behave. So we have multiple systems. We have the logistics, we have the supply chain, we have the production, we are purchasing, how all of these systems are going to play a role, how they are going to work together, and how they are going to deliver. So all these can be simulated and validated upfront. That's the greatest advantage that we'll be seeing because of these VPPD tools. So now with every piece of information is validated, now the process designers can start documenting them. The documentation can be in a 3D form. So since it is in 3D form, the training becomes much easier. The operators who are going to produce these products, whether they are fabricators who are going to weld, or there can be machinists who are going to machine certain parts, or if they're going to be assemblers, everyone can be trained using these tools. So in fact, we have done several exercises in the past where we have called people from marketing, dealers, service engineers, and using that I-see-I-do environment, the immersive environment, we have trained the operators on how to build the machine, how to service the machine and all those. That's the greatest advantage using this tremendous visualization capability that these tools possess. So the same can be extended for the shop floor, where the documentation, as I mentioned, can be a visual aid, or it can be in a 3D PDF format, or it can be a video of a particular process sequence. Anything can be created, and using execution systems, we call it as manufacturing execution systems architecture, MESA. Using those execution systems, those things can be deployed across the shop floor. So at every stage and every station where the machines are being built, operators can go back and refer to the visual aids and perform the task accurately every time. So all these helps to bring the machines to the market in the least possible time. That's the greatest advantage that we can see both on the product side as well as on the process side using these VPPD tools and technologies that I mentioned. Thank you. With this, I'm going to hand it over to Subbu. He will be taking us through certain case studies, how companies have got benefited at different stages of the process. Over to you, Subbu.
Thank you, Murari. This is Subbu, and based on what we had seen in the previous steps, whatever we could do virtually uh, on each stages of an NPI cycle, we had tried to consolidate few examples which had taken care of most of those steps to virtually prove the product as well as process as well as plant, all of them, and has helped them in taking decisions and getting the product to assembly line and to market on their launch dates or even earlier as well. Okay, so the first case study that we are seeing is basically on a product design point of view. Okay, so this case study is for a heavy construction and mining industry company, and they utilize these virtual tools almost on every NPI cycle. Okay. And this case study was taken for just one of the heavy construction. Is it fine now, Ron? Okay. So in this case study, we had taken a mining truck, which is part of an NPI cycle, and we start engaging right from the design phase. So initially the model would start at a 50% level, and then it would the actual engineering model would get matured over a period of time. So we start engaging in level of 80% confidence level. So the maturity level of the product should be about 80%. because that's when you'll start all the systems coming together, and we'll have all the parts that need to be in that particular product. So in that stage, the virtual tool, what it does is we review the model and make sure the model is closer to the actual product that's going to be manufactured. So the intent of that particular activity is to make the actual product as well as the 3D model to the near perfect condition. It should be almost the same. So including the wiring harness routings, the hose routings, and whatever the flexible parts may be, that also we take into account, so that even in the model, it's not uh, actually interfering or going through a component. Okay, so in that particular stage, there are about 24 checkpoints that fall under various categories. So the few important ones are making the part duplication, eliminate those, and the unused parts. So usually what happens is, in each stage, the engineers work on systems. So the engine systems, hydraulic systems, electrical systems, and they take reference part of previous system and start working on their own system. So when all the systems come together, that's when the product would have duplication of parts, or parts that are not used, or probably that are not in the right location. So that's when the concurrent product and process engineering really takes into kicks into its actual work. Okay, so that's when we'll take into account or identify the issues like the part duplication, unused parts, and there are sometimes cases of thread mismatches. The thread engagement length has not been met based on specifications, or parts not being assigned at all, or a wrong part has been called in a particular location. So there are 25 different categories through which we fix the model, and those feedbacks have been given back to the design engineers of particular system, who will go back and change the drawings before models before they actually release it into actual PLM, or in Creo environment it will be Windchill, or in Siemens environment it might be Team Center Engineering. So before the drawing is being released, we fix all these. Okay, so that is the first stage, which is the fixing of actual model to the reality. And the second part of is the actual design review on various can you go once yeah. Okay, so in this case what we do is we take the design or the model, and by this time the model would be about 90-95% accurate to the actual reality, and then we start creating the actual manufacturing bill of material. So there will be an engineering bill of material, and now we have started creating the manufacturing bill of material. So based on a particular assembly or a country or an assembly layout that it's going to be assembled in, we take that as reference. So in the, it can be a multi-model line, or it can be a similar kind of product running in a line. So we need to take into account the current steps that are being adapted in that current assembly line, and not deviate much, so that this particular model would go into that particular assembly line seamlessly without having any issues. So we create the manufacturing bill of materials based on the actual assembly sequence, with the number of operators or the number of stations that it's going to adapt to. And on those account, we start analyzing the model for its manufacturability. So we call it design for X. So X can be for design for assembly, design for tooling, design for ergonomics, design for serviceability, design for transportation. So there are about 18 X's are based on which it revolves around. So we take into account even the lifting device that might be using, and perform a particular task like the landing study that you're seeing and the tooling and ergo validation that you see. So we model the tools that are going to be used in that particular assembly line, or in case it's being using standard assembly tools. So we could download those particular CAD models and use it to see whether that particular design would be capable for assembling. So based out of that, we will be giving the feedback to the design engineer saying, okay, we have issue in assembly. We'll have a tooling issue when it goes to the assembly line. And an operator would not be able to perform, as you see in the top bottom right corner, the person is trying to reach out a bolt which is probably down, and he might not be able to reach it. So those kind of situations are being virtually simulated, wherein the ergonomic study will say whether the particular operator could be able to perform that particular operation or not. Okay, so these are being fed back to the engineer. So as you see, can see the outcomes. Uh, the issues are being categorized as critical and mild. So the critical ones needs attention and probably calls for a design change. And the mild ones are probably you can do good with slight modification, or if the operator is performing that particular task in a probably once in a single day, so he could go ahead and do it with slight discomfort. So it's up to the process engineer and design engineer, even the plant engineering, to decide whether it's a real issue or not. Okay. And on process engineering count, so all those tooling issues and ergo issues would have to be addressed, because without tool access, probably we'll not be able to perform that particular task as well. Okay. And the ergonomics is probably one of the things that it's a standard that he should not be having any discomfort to perform a particular task. So there are standards like he should not be uh, lifting a particular component above 8 kilos by hand. So he should have an assist like a lifting device or a spring balance or an jib crane or those stuff. So all these are being fed back to the design engineers, and they work on that particular model, and it's an iterative process. It goes in few stages. So based on the model maturity and fixing of all these issues, the product is being released only after all these criticals are being addressed. Okay. And once it's being released, it's probably near perfect for actual production as well. Okay. So that's what this particular example states. Next slide, please. Okay. So this is another example wherein we worked for field assembly. Okay. So the problem statement here was the particular machine or the trucks, off-highway truck, in field used to take 20% more time than a competitor to remove and install the engine, leave alone the actual probably the service of that particular engine would be based out of probably the defects or what is being identified. But just for removing as well as and installing it, the time taken was about 20% more than the competitors. So the task was to reduce the timing probably by 25 or even more than that. So in this case, the actual process that was adapted was creating the actual removal sequence and install sequence of that particular engine as done in the field first with that particular model. Okay. And we cannot straight away jump into a solution. Okay. So we need to validate whether they are doing that particular time on an efficient timing or not. So we did a time study. So as Mr. Murari suggested, various time standards. So this company had their own time standards. We did that time standards and arrived at a particular percentage. So that standard was initially not met. So there was certain percentage of time that was taken, which was more than actual standards. Okay, so in this case as well, we need to consider the efficiency as well. So and fatigue and the shift timings, all those stuff. Okay, so all considering that, we do a time study. Then the activity involves suggestion of a removal sequence. Probably in this case, it was a modular removal sequence. So probably the engine can come along with the radiator and along with the transmission. So all those various options, whatever could be clubbed. So if you limit the number of removals, you reduce time drastically. So in this case, we suggested few options that can be adapted, and what will be the design change or requirements for all those particular options. Okay, and all those particular options were supported with a respective time standard and how much time it would take. So eventually, all the scenarios, there was one which actually would reduce the time by 42%, which is almost like 20% you are going above of what is required. Okay, so it doesn't stop there. So the one of the it did ask for a design change on that particular product, and actually those were accepted, and it is under trials right now under design changes. It happened pretty much last year or so on. So what happens is we do not stage ourselves like, as a virtual engineering does not stand just by giving option. It gives even the sequence in which you can build it, remove it, and you can install it. And what would be the tools required? And what will be the man hours that would take to perform that particular task? And how do we balance it? And what is the removal as well as installing standard work document? So basically it would cover what and all he should be doing, what and all he should be taking, and what tools he would be using. Basically, if he reads it, anyone could go ahead and perform those particular tasks. Okay. So this actually reduced by 40% by performing the design change, and it was a huge achievement at that particular time. Next example, please. Okay. So this is one of the examples wherein a facility layout, basically there was no, uh, it was a green field, and the requirement was to build the excavators. Okay, and they wanted the virtual engineering to work with them right from the concept stage itself, wherein they need to do a space claim analysis and do capital budgeting. So in that case, the virtual engineering helped them probably first time to visualize on probably what will be the time, how much would be the number of stations, what would be the space that they might require, and with all the requirements like the testing, the painting, the field test, even the yards, all those taking into consideration, we could arrive at a capital budget. Okay? And then you could create a functional layout. So first, uh, it starts with 2D, right, in the past. So nowadays it actually starts with the 3D itself. You have the CAD models, and you would have the facility which is reference, and you have the standard pillar distances, walls. Probably you can select the heights and stuff based on your product configuration. So on those lines, nowadays the functional layout happens in 3D itself. and that gives management a better understanding of how their layout's going to go look. And basically the in the past there have been like what is being required is being proposed, and what you receive from the management on the capital budget or on the space requirement is way different, and you probably end up working with the constrained environment. But in this way, it's easier for the engineering team or the process engineering team to actually convince the management on what they are trying to achieve. So what is the functional layout and why do they need this much space, this much budget and all those stuff. Then comes the detail layout. So wherein you actually take into consideration the virtual. So initially we start as a discrete event simulation wherein you need to get the output, right? So eventually we need to get the output. What will be the optimal number of operators that would be required, optimal number of stations, material handlers, how the logistics would perform, what will be the timing. So based on that, a simulation will be run, and we can get the results which would be almost 90% to 95% at this stage to the actual reality. Okay. So once that detail comes, then a detailed process sequence like the manufacturing bill of material or assembly sequence is being written is sequenced in the virtual environment using the CAD model, and that creation is being fed into the digital factory, because based on the throughput outputs, we would create a 3D layout wherein we can actually place that particular component and virtually run the process sequence and layout and prove it to the process engineering and management on how it's going to look like. And basically we can validate the actual process using the tools that they would be adapting or the material handlers that they would be adapting. What will be the forklift path that they would be going through? Where would the parts would be? Will it be easier for the operator to actually take that particular part? Is there a crane reach? Is there interference on the crane to the top height of that particular product? So all those validations are being done and performed and proven. So next stage is the uh, prove out to each stream of people. So first, initially it's the management to get the approval of that particular design of how the factory is going to look like. Okay. That's stage one, wherein you have the virtual walkthrough animation. Stage two is the process engineering, where we prove that particular assembly sequence or that particular product in the particular factory itself on how it's going to look. So digitally we'll be proving the process and showing what will be the critical areas and how are we going to mitigate them. Then comes the operators. We call the operators and train them on how the particular operation is going to be performed and what will be the critical areas that they might have to take into consideration. Then comes the work instruction. So the work instructions are being provided, as Mr. Murari suggested, in 3D PDF or even in animation, it can be provided. So after all these stages, we would have a 3D layout, a functional layout, and a proven layout, which is ready to be deployed. So this helps us to actually support the actual erection process as well. Like where would the electrical points would be, where will be the water lines would be, and where is the trench that we need to have, and what will be the route that the electrical lines would follow. So all those can be seen in the virtual environment, and basically during the prove out, this helps in prove out as well. So in this case, we have 95% success rate first time right on each particular layout. It can green or brown field or even the process improvement. The 5% is not due to the layout. The 5% had been due to the parts not available or the tool not available. So basically we, on process front and layout front, we have a 100% track record first time, right? So these virtual tools basically helps in solving each and every problem that we would encounter in the actual layout, which will be during the iron build. So next example, please. Okay, this is one of the examples wherein the existing facility had to be optimized for the right output. Okay, so basically it starts with digitizing the particular factory. So in this case, and most of the cases, the 3D factory is being modeled using scanners. It helps get the dimensions of each particular component or the asset and model it based on the functionality. So if it's a press, then the RAMs would be flexible to actually validate a new component which might come in future and whether it would fit that particular press or not. So all the digital factories are modeled functionally. So it can be used for digital validations later on. So in this case, the entire facility was modeled in 3D, and then we ran a 3D discrete event simulation, wherein we identified the flows, basically the ton meters of that, but it's a machining layout and a fabrication layout. So in both the cases, the products were huge, and the heavy product should not be moving for a longer distance. That's the main criteria. So by introducing cell concepts and by rearranging the movable assets and scrapping the ones that were not providing the uh, right efficiency, these layouts were optimized for the floor space as well as the overall flow, decrease the ton meters of the particular of the components inside that particular assembly line, and basically it unlocked space of about 15% for future as well. So the current layout space that they were utilizing, we were able to achieve the targets by reducing the space, and even we accommodated 6 new machining centers inside that particular line, which they had ordered. So basically, the digitization, discrete event simulation, virtual validation, and prove out everything was involved to achieve those particular results. Basically, they didn't have to go for any new bay expansion or extension of the base. Next example, please. Okay, so this is one of the examples of factory transformation. So this particular product was manufactured in a different country, and this was transformed to another country wherein the number of stations that they were provided were reduced from 13 to 5. Basically, they had 5 stations instead of another region where it was they were using 13 stations to perform it. So in this case, it was basically running the process sequence for the available space, optimizing it, and accommodating, achieving the tact based on the particular demand, and offload the mainline activities into subs or probably to the suppliers to ship us the finished goods itself by subassembling at their end. So all those strategies were worked out to actually get that particular product manufactured in that new country on a 40% space of what they were usually utilizing in the other country where it was manufactured. So basically it was working with the layout as well as process, as well as suppliers, logistics as well. So entire suit came at, you had to analyze it, and we need to actually make sure that particular layout change or the process change is feasible in virtual environment, and then bring it to reality. Again, in this position, for this product, when the layout was erected, all the components were received. We had a first time right in this product as well for the first 5 machineries, and even the um, online support of that particular we usually uh, the virtual environment calls for a physical presence during a try pilot build or a tryout. So an engineer has to be present, and the people who had virtually worked on it would pass on the data, and it will be easier for the person right there to actually uh, guide on the sequence or the builds. Okay. So that this had basically everything covered, right from process design, layout design, logistics, and discrete event simulation as well, all being virtually proved out before the actual iron build. So that pretty much sums up the case studies. But if you would like to know more, we could have some more case studies as well discussed. So, since we'll be having a contact details of Sanjay over the end, you could get in touch with us for probably more insight on probably specific areas of application. So basically, to summarize everything, um, the virtual product and process engineering would avoid late changes post release. Basically, we are trying to reduce the number of releases of the drawings. So by anticipating the failures before the model actually gets released. So that would help save lots of cost and probably achieve the desired results on the actual plan. Fewer design and process changes later in the product development process. Basically, we would be reducing the process changes that would happen in the assembly line or probably in the field. By virtually proving it and prepare documents or visual aids to actually help the operators perform by the sequence suggested by us. So on-time quality product at lowest product by doing virtual engineering, we most of the time we would be hitting our NPI timelines more most of the time, or even lesser as well. So when the product comes out and the first build might be a proto or a pilot, basically in this heavy construction and mining, most of the NPIs have started going directly to the product and directly to the assembly line itself. It doesn't require a separate space to actually perform those particular pilot builds or proto builds. It goes directly to the assembly line. So by doing that, the cost of probably investment on a particular space, assets, operators, all are getting released, and it's almost assembly line ready in the first time itself. By performing virtual process planning, actually we find the risks earlier itself, and we could work on probably how to solve those issues by doing brainstorming and getting the expert opinion from various people. and we solve it before it goes to the actual production. So the legacy capture and reuse the past knowledge and the tribal knowledge, basically the knowledge that is not documented anywhere, all are being utilized uh, to develop a particular product which would be innovative or probably not thought of. It would be design ready for manufacturing, and it would have lesser number of changes when it goes to probably assembly line, and when it goes to field testing as well, you will have a better result than the past way of work. So that's about it. So we are open to your questions, your suggestions for any future references, case studies, or anything. You could get in touch with Sanjay, and we have his contact details right there.
That's great. Thank you very much, Sabu, and the team from Axis Caddis. Prior to meeting Sanjay, I had no idea a lot of these tools actually existed that allowed things that we used to do after the engineering drawings were released or after we started to cut steel. I had no idea that the tools existed to actually drive a lot of those activities before that, and the capabilities to be able to go through training sessions with employees prior to assembly stations being developed, and very, very powerful tools. And like I say, I had no idea this even existed. So yeah, thank you to the team from Axis Caddis. If you have any questions, please use the Q&A feature down on the bottom there of the webinar. I'm going to start off with a question I have is, once a process from door to door within a factory is modeled, I would assume it's fairly easy to run what if scenarios. What if I move a certain portion of an assembly offline to a sub-assembly station? Can you actually see the effect of doing that on stations before and after, and on the takt time of the entire production system? Is that possible?
Murari here. I am going to take that question. That's a wonderful question that the participant has asked. Yes, it is possible. So within the four walls, whatever that is happening can be converted into a 3D model, simulated and analyzed for performance. It's possible with whatever the tools that we have already mentioned. For example, if you want to create a 3D model of the factory environment, we have tools like the Autodesk suite of products that Inventor has got an add-on onto that, or we have Factory CAD, which is a Siemens product, which really helps us to create a 3D model of the factory environment. Once it is ready, we can start visualizing each and every operation, and using discrete event simulation tools like FlexSim and PlantSim, we should be able to mimic the real world conditions. So we can create the current state scenario, validate the mathematical model for the results. So the mathematical model which you create can mimic whatever process that you have. You can include the mean time to repair, mean time between failures, whatever issues that you're going to have in the shop floor. You can also incorporate the efficiency of the operators. Everything can be done inside the mathematical model, and you can run the model for a certain amount of time. So the first step in the process is to create the as-is scenario. So with as-is scenario, once you start seeing the results, you will gain a lot of confidence on the model accuracy. Then it becomes easier for you to do your future state model. We call that as if model. So for the as if model, you can incorporate whatever changes you want, and you can run the model for a specific time period for a given demand, whatever it is. And it will help you identify what would be the throughput, what are all the bottlenecks that you may encounter, what would be the possible utilization that you can achieve for resources, what would be the optimal material flow on which direction it has to flow, whether there would be any congestion on the aisles. All those can be simulated and understood well in advance within the shop floor. Okay, thank you
Excellent.
for the.
Excellent. We have a question from Bob Hastings. He asks, recognizing that there'd be great variability for a case study 3 type facility layout, engaging with your company, how long does something like that typically take? And do you have a team, do you plant a team in Winnipeg to do it, or is it all done remotely?
Yeah, we can do it remotely. I think Subbu can answer that better than
Yeah,
me.
yeah, I'll take that question. Actually, the typical digitization of a factory would depend on the asset that we are actually modeling, number of assets, and the accuracy and the functionality in which those assets have to be modeled. Okay, so for an example, the case study 3, the functional modeling was on few particular assets, like the rams, press rams, and probably then the conveyor. So only those were taken into account. So on those lines, that particular facility took about 3 months for modeling. It did had assets. On a particular bay, you might find 15 to 20 assets. Okay, and there might be duplication of those assets on the next bay as well. So taking everything into consideration, the time would vary on a detail level, or probably the accuracy of modeling, the functionality, and the number of assets. Okay, that's on digital factory front. But if we take the optimization activities of that particular layout, so what are we trying to achieve? Probably increase the throughput, optimize the line, increase the efficiency of assets, increase operator efficiency. So all those would depend on the number of assets that are being utilized and modeling a particular assets model and creating the feature state. So that might take from a simple modeling to a complex modeling. As I said, even it also depends on the model on which we are working and the number of part numbers that we are working with. So basically it takes into account every part number that goes into it. It forms as an assembly and moves to the next station. So taking that account, it might take from 2 months to probably 6 months based on the complexity. And yes, all those can be done offline, but a periodic interaction with the on-site team or the process engineering team or whoever is probably a single point of contact for that particular goal that has to be achieved has to be performed, and uh, all those consideration would be a concurrent one. So basically, we would not come out directly as a single output. So there will be suggestions and there will be inputs considered from even the uh, customers or probably other who would have better ideas as well. So collaboratively, the layout would be performed, and most of the time it's a collaborative effort. Okay, it's not like you get a problem statement and you solve it once. As we understand, same particular operations, if I say 10 series of operations, it could be done in 5 different ways and all of them would be correct. Okay, so what fits best for that particular facility and the operators would come only by collaborating and providing the facts and data for that particular output. And we discuss over the facts and data and come up with the optimized solution. So it's basically a collaborative effort. And it can be done offline most of the time, but probably frequent visits or probably write video out inputs in case there are concerns, The plant engineering would have to support by providing documentation or probably videos, anything on those concerns.
Okay, that's great.
I hope I had answered the question.
Oh, thank you, Sabu. One of the questions I had was a lot of the manufacturers here build product that varies in timing. You take a bus manufacturer, for instance, if a customer adds an option to a bus, it could dramatically increase the amount of labor in a particular substation, but the one behind it may not have that option. The one behind it, or the one behind that might, the one three behind that one might. So there's variabilities in timing, and you kind of have to look at the production as a system more so than individual line stations. In a virtual world, are you able to work with that product and timing variability in order to come up with best case scenarios?
Okay, I'll take this question. Hari here. So it's possible. Whether it's a single product line or a model mix, it's possible to incorporate everything into an assembly line, and we can simulate that situation using discrete event simulation modeling. There are case studies where we incorporated two different product lines, two different product families to be precise. Okay, so one a feller bencher and another, both are forestry machine. So two different product families, we integrated that into one single line using these advanced tools. So we simulated the conditions because both the product family should be moving on the same assembly line, but each will have their unique work content. So we identified what are all the activities that can be performed on the line side, what are all the activities that can be performed on the sub-assembly side. All those were done upfront and validated using discrete event simulation techniques. And we also, to take this further, actually I understand that each bus bodies are unique and are custom built. So it's all made to order. So, but there are, every mission has got certain level of standardization. So using variant configuration methodology that is very prevalent on SAP and other ERP systems, we can identify what are all the standard parts, what are all the variant parts. We can create a positive bill of material. And for the worst case situation, we can simulate and provide the results so that the easiest product can be manufactured. The product which has got the lesser number of variations can be manufactured very easily, and still the same line can take for the model which has got the most number of variants. So all these are possible using the tools and technologies that we have today.
Excellent. Thank you very much. So it is 10:30 and we don't want to go past that mark. I thank you, gentlemen, for the presentation today. It was very eye-opening. Like I said earlier, I didn't know a lot of these technologies, virtual technologies existed. And, you know, now that we see the impact of these technologies being able to drive a lot of the production planning and standard operating procedures and all the other things that are required to produce a product earlier, I can certainly see how this would speed the time it takes to get a product from concept to production. So Sanjay and the good people at Axis Caddis have offered to send out the slides to anyone that is interested. So please contact me by email if you would like those slides. And yeah, with that, we will end today's presentation. You have Sanjay's contact information there on the screen if you wish to contact him directly, if you have questions specific to your application. We are also recording this session, so we will be posting it on our website for future reference. So thank you to all. Thank you to our presenters. Thank you very much for your time today and tonight. And we look forward to the next VTC cluster technical meeting. Thank you very much.
Thank you, everyone. Thanks a lot. Have a great day.
Thank you, gentlemen. Have a nice day.